What's going on, everyone? Welcome to my channel where we talk about everything finance and tech oriented, and today we are going to be talking about a gated recurrent unit, or GRU for short. Now, before you even start watching this video, I highly recommend that you check out my other video, Recurrent Neural Networks, because a GRU is essentially a build off of, or like an improvement of the recurrent neural networks, and everything that you see in this video is essentially built on the work of the recurrent neural network. So I highly recommend that you check that out. And before you forget, make sure you hit that like button and click on the subscribe button. That really helps out with the growth of this channel, and you get to see more of me. There could be two parts to this video. The first part, I'm going to be going over the theory and how a GRU works from a algorithmic point of view with all the equations and some visuals that are in the slides that I created. In the second part, I'm going to be going over the basic idea on how to apply a GRU to everyday data. So let's get to it. Alright, so let's begin with the gated recurrent unit. This model was acting as a supplement to the recurrent neural network. It's basically like an improved version of the recurrent neural network. One of the issues of the recurrent neural network was that there was a vanishing gradient issue where the weights of the actual model were not being properly updated, or there's just no change with the weights at all. And this happened because the RNN usually just forgets what it's learning, and it keeps on just inputting the data into the overall model, and there's just no learning happening there. At least that's one of the ways that it forgets what it's doing. So that's why we have the GRU, and it has two different weights. It has a reset gate and an update gate, where it determines whether or not to forget data or remember data based on the given inputs. And it essentially utilizes two different logistic regressions, and it determines whether or not the data that's coming in is useful or not. And this is a simplified version of the LSTM. The LSTM has 3 gates and the GRU has 2 gates. And there's different pros and cons to which type of model to use, but in general, there's not really much of a difference in terms of the output that's coming from the two models, except when it comes to like speed. So GRU, since there's less parameters in the GRU, it's easier to train and it's just faster to compute. And this was for like a long period of time, this was like the choice model. However, it really just depends on just the type of data that you're using, because based on what type of data you are using, the LSTM could prove better than the GRU and vice versa. So it's really by a case-by-case basis, and make sure you always compare the models with each other. This might not be ideal if you have huge models. That's why you just gotta subset it and work from there. So the overall architecture of a GRU, as I mentioned earlier, we have an update gate and we have a reset gate. And let me get my laser pointer over here. Laser pointer. Yes, we got an update gate, we got a reset gate, and we also have the hidden state. And these are all going to be used in order to calculate the next portion of the given model. And this is very similar to the recurrent neural network, where we essentially just matrix multiply your hidden state by the weights of the hidden state that's going to go to your Y parameter, and that's essentially your prediction. So if this is a little bit blurry to you, I highly recommend just checking out that recurrent neural network video. It'll just bring you up to speed. So let's begin with the diagram. So initially, let's break down this model, because initially I thought this entire diagram was very confusing, and but once we start to break down the components, it becomes more sensible in terms of how everything works. So this is actually very similar to how the recurrent neural network is formulated. The only thing that's different is how it computes the hidden state. And so yeah, we have over here, we got the reset gate, as denoted as ROT, and we have the update gate, Z_T. And we can go a little bit deeper into that. But if you already understand this in this diagram, it's 100% understandable. Feel free to skip to the code. It's very similar to the RNN stuff. Let's begin with the first diagram. First, we notice that we have our hidden state, our initial state, which is usually denoted with a vector full of zeros, and we have our input data that's going to be coming on in. So the very first step is going to be our reset gate, and this is this portion right here. So the reset gate is defined as some activation function, usually like a sigmoid, and we have the weight of XR denoted here. So we have this X of t going to the branch. We have the weight of X to R I try to make it more sensible from the previous video. So we have the weight from X to R that's going through here, and we have the weight of H to R. So that is seen over here. So the weight of H to R. So we got this branch going on over here. So there are multiple matrix multiplications happening. We are multiplying the weight by the given input, x underscore t. We add that, basically just do like a sum product. We add that to the weight of h to r over here, and we are multiplying that by the hidden state here. And then we add some bias to this layer, and that is our reset gate over here. And notice that if you were to look at the overall architecture of a logistic regression in terms of like a neural net type of like architecture, this is actually just like a logistic regression over here. It provides you a probability as to whether or not it's going to go to like 0 or 1 essentially. So that's where that's activation function here is more or less a sigmoid. But yeah, that is essentially your reset gate here. The next step is going to be our update gate. So this is actually very similar to the reset gate in that it's another logistic regression, except this is usually determined, this determines what data to keep in, and that'll be more clear for the candidate hidden state, which I'll be going over very shortly. So we have the weight of h to z, which is this branch over here, h to z, and we have the weight of x to z going over to here. So there is matrix multiplication, the weights, you multiply that by your input, x to z by your x underscore t, and you add that to your weights of your h to z, so your initial state, or h underscore t minus 1, you multiply that by the weights over here, and then you add some bias. So that is essentially your update gate. And so this is where it gets really funky with all of our units just basically being mashed together in a way. So the activation function is usually a tanh, but you can definitely play around with that, whatever hidden state activation that you would want to do. But this is where my blue weights over here, we got the weight from hidden to hidden states, and you got the weight from your input to your hidden state over here. So this is where you are essentially, you retain your previous memory, but you're adding essentially what you want to forget or remember. So that is where your r underscore t comes into play. So if your reset gate is very close to 0, meaning you don't want to remember that, then correspondingly your hidden state, you can multiply that by 0, it's going to be 0. And then if you multiply your 0 by your given weight, that's also going to be 0. So there's no updates that are happening here. So that's where the reset gate comes into play. And so the last part is where your update gate is going to come into play. So remember that your reset gate and your update gates are essentially two probabilities, whether or not it's going to go to 0 or 1 based on the sigmoid activation functions. And the 1 minus the probability of your gate remembering something or forgetting something, right? That is what you are going to be retaining for your overall model architecture. So going back to the diagram over here, we have 1 minus your z of t, your update gate, 1 minus z of t, times, right here, there's an X mark, just times, you multiply that by your hidden input over here, your hidden state, t minus 1. So that is where this comes into play. And then you're adding your update gate, and you multiply that by your hidden, your candidate hidden state. So that is denoted right here. So there's an addition, and then you're multiplying your reset gate, your update gate by your candidate hidden state, and that is where your overall hidden state is coming to play. So we have one branch over here, another branch here is going over here, and that is your h of t, and then the process just continues. The h of t, in order to calculate your prediction, you just multiply the weights of your hidden vector, and then that is your predictions from there, and then it keeps on going and going and going until you run out of epochs that you want to do. So yeah, that is essentially what the architecture and theory of a GRU is like. It's very similar to that of a recurrent neural network, and also very similar to an LSTM. Okay, so this is the code for the gated recurrent unit, and notice that throughout this entire demo, my notebook demo, it's the exact same code of a recurrent neural network. So if you want to get into the nitty-gritty details on how I'm cleaning the data, do check out that video. I don't really want to make the the information redundant. So just make everything clean and concise. But I'll just be briefly going over on what I've been doing in case you haven't really checked out that video. So over here, load in the libraries. You got your data science ones. You got your pandas data reader, which I'm reading the financial data from. And there's like a really neat web scraper data extraction video that I've done, and the little bubble should pop up down there. Got your plotting packages, your scalars. I'm using TensorFlow. I got a 2.4.0 over here. Set the random seed to something so that it's reproducible. If you want to use the same seed, go for it so we can get the same results. Load in the data. Today is December 27th. Happy holidays, guys. But essentially I'm getting 5 years worth of data, get that into gold, name that's gold. We can get the adjusted closing. That's what it looks like. Didn't really change much from last week. Get the percentage change, which we'll be using for the univariate, and then this stuff we'll be using for the multivariate predictions into the future. So store the corresponding values. This is going to be used a little bit further down the road. We are going to be using the univariate forecast for a GRU. We'll be using the same idea from the previous video. We got our returns. We're predicting the returns based on its own historical data. Something that what the returns look like, which does make sense. It's surrounding 0 because you might not be making anything on a day, but you can be making as much as 6% on your money or losing as much as 4%. So that's like the range on there. That is not included if you're doing options trading, but you know, we got a histogram on what our returns look like. So if you want to do some like normal kernel estimations or some other fancy model, feel free to do that. But this is where I'm just cleaning my data set. I'm flattening everything into an n by 1 NumPy array. Scale that NumPy array using some scalar that I've imported in min-max scalar. Got 1329 observations that I have working with. And then this is where I'm just cleaning my data. I'm using 10 historical observations to predict one step ahead. And I'm just storing that to X, and then my Y observations, my predictions, I'm storing that into Y. And I got my data lengths and what those data look like. And then I'm just getting the dimensions after I convert everything to a NumPy array over here. And the threshold is 1187. 90% of my data is training, 10% is testing, and the threshold is just the value that I'll be using to discriminate the two. So this is where the only thing that's really much is different. I have a GRU over here. So based on the theory that we went over, the activation function, this is going to be the very last value for our candidate hidden state, and just combining everything for our hidden states. The recurrent activation is the sigmoid. That's where the idea comes from, which memory to retain and which ones to forget. And then our input shapes, that corresponds to number of observations that we're plugging on in from our X, and the number of features, which we are, since we're only working with one variable, it's just going to be 1 right there. And then, you know, some penalization happening. We have a regression task over here, so I'm just using one dense unit, and I'm using Atom and mean squared error, and that's the architecture over here. So it should be really fast to train. 100 epochs, 32 batch sizes, and validation split 20%, and verbose is 1, so we can print all of that stuff out. So wait for that to print on out. And I go a lot more in depth onto what everything is. Everything is explained in that recurrent neural network video. So yeah, and then once we have trained everything, this is going to be the loss. So our loss is actually doing pretty good. Wow, that's actually kind of surprising. But wow, yeah, that's yeah, it's actually really good. The training and loss, essentially you want them to be very close to each other to have like a somewhat of a good prediction. Otherwise you're going to be underfitting, as I noted as my notes over here, or if it's overfitting based on that condition, if your training loss is much less than your training or your validation loss. But over here, let's go on to the next stage. So if we want to do some forecasting for the univariate, this is where the sliding and rolling approach is. Big idea here is that you are essentially using your most recent X value to plug in as your prediction to get a predicted value, and then you're using that predicted value to plug into your newest input, and then you chop off your oldest. So that's seen over here. Once you have your prediction, your model predicts something based on your most recent input, your latest input denoted here. You are, just storing your p-value, which is your most recent prediction, but you are also plugging this prediction value over here, where we are getting the very first. Remember, Python starts everything at 0, so we're starting everything from 1 to the end of our array, and then we are appending the p right next to it, and we're chopping off that oldest value. And then it keeps on going, and that is what our predictions are doing, 132 of those forecasts. And this is what our forecasts look like and compared to our true value. Notice that not everything is scaled. It's still in its original format, but if you really want to make money, for instance, then you probably want to take that into consideration, just like scale everything and then bring everything up. But the most glaring part is that we are essentially just using the same value as a prediction, and then it's just going through. That just means like your model is not as robust, and your prediction, the average prediction, which looks like 0.45%, that is what you are expected to make on average. So that is like the best prediction that it will be doing for this given particular model with its given parameters. So if you want to add some other variables to that, you could probably make your model definitely a lot more robust. Maybe have some, I don't know, like some sentiment analysis via NLP, or you could have some exogenous variables that may describe what's happening, like supply and demand based on a quarterly basis, stuff like that. But next step, this is the multivariate forecasting. Same idea, except we are getting we're actually getting 4 different features: the high, low, open, close, and volume. So that's 5, my bad. We're using all of these 5 values, these 5, to predict the adjusted close over here. Same idea, we get the 10 samples as our historical data, and we get 1 observation 1 step ahead to predict that. So this is the 1 step ahead training part, and this is just cleaning up the data set, and that's what it looks like. We should have 5 observations, 1, 2, 3, 4, and 5 as a representation of high, low, open, close, and volume. And then our y value over here is just going to be our value for adjusted close, and that is starting at 0 plus samples, so it's going to be our 10th value. And so using the previous 10 values, 0 to 9, we want to predict the 10th value, so it's always 1 step ahead. That's like what the rolling window is. Convert everything to a NumPy array, get the training and testing sets and dimensions over here, and just store your data into corresponding train X, train Y, test X, test Y. And then over here, I'm using a GRU of 15 units instead of, I think I used 3 over here somewhere. Yeah, I used 3. Yeah, so this could be a little bit more complex since we have obviously more features to work with. And hopefully our model does not memorize the entire thing, which it probably is actually. Let's run the training, same thing, 100 epochs, 32 batch size. Validation split, 0.2. Yeah, let that run. But the overall idea of just utilizing machine learning, especially for like regression type data, very similar. Once you understand the architecture of whatever model you are using, the data part comes like really easily, and just like you have your inputs and then you try to get an output. And then this is what the plot looks like. So we have some squigglies happening. So the training loss is a little bit lower than the validation loss, which signifies over here that there's some overfitting, so there's potentially some memorization happening. And what I mean by overfitting, that just means that like if you have 1, 2, 3, 4 as your dependent values, the next value might be 5, right? So every time you see that pattern, you're always expecting a 5, and it's just memorizing that, which is not necessarily a good sign. But this is our predictions for our 1 step ahead. Notice that it actually looks pretty good, but this is one of the factors of just utilizing time series, since everything is very dependent, and since especially this is 1 step ahead, the values are bound to be very close to each other. And you would have to take that into consideration too. So this is not the golden grail model to use for, your stock picking or your day trading, right? There are different techniques, and there's other observations you would probably have to take into consideration, especially the news. But yeah, that is essentially my code demo on GRUs. I hope that you enjoyed this tech demonstration. It's very, very similar to the recurrent null networks in terms of the ins and outs. The only thing that's different is how it calculates the hidden states. And GRUs are definitely actually a lot better than the RNNs because it takes into consideration of that vanishing gradient problem. It's also very good for if you want to do some NLP analysis, some text memorization, quote unquote, and prediction. This is also very much used in that world. So key takeaways: GRU is great for learning what type of data to take in and take out, and it's more robust than that of the RNN.